Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good day. We shall continue our discussion on the topic of rocket propulsion. So in the previous two videos, we have gone through the total impulse, specific impulse, propellant mass, and effective exhaust velocity. And then we continue with the second video, which is the looking into the mass ratio, propellant mass fraction, impulse to weight ratio, and thrust. And this particular video, we will look at total thrust as well as the exhaust velocity. When we talk about total thrust, for a steadily operating rocket propulsion system moving through a homogeneous atmosphere, the total thrust F is equal to expression 14. It can be expressed in terms of the mass flow rate times the velocity, which is the momentum thrust, plus the pressure difference, P2 minus P3, times A2, the area in the nozzle chamber, okay, which denoted as the pressure thrust. The rocket nozzle is usually designed that the exhaust pressure is equal or slightly bigger or slightly higher than the ambient pressure, which is P3. So when we look into the vacuum space, we know that P3 equal to 0 and the thrust becomes expression number 15, which is equal to the momentum plus the pressure in the chamber times the area in the chamber. So the pressure condition in which the exhaust pressure is exactly matched to the surrounding fluid pressure, where P2 equal to P3 is referred to as the rocket nozzle with optimum expansion ratio. Equation 14, which shows that the thrust of a rocket unit is independent of the flight velocity. Because changes in ambient pressure affect the pressure thrust, there is a variation of the rocket thrust with altitude. So since atmospheric pressure decreases with increasing altitude, the thrust and the specific impulse will increase as the vehicle is propelled to a higher altitudes. So this change in pressure thrust due to altitude changes can amount to between 10 to 30% to the overall thrust. So figure 2.2 shown here, which is the altitude performance of a typical RS-27 liquid propellant rocket engine used in early versions of the Delta launch vehicle. So you can see here in terms of the altitude, okay, we have the altitude in feet times 10 to the power of 3, right? The specific impulse 2.55 seconds, starting with 2.5 seconds to the 290 seconds. At it increases, okay, it increases, right, as the altitude increases. Similarly with the thrust, from 188,000 pound thrust, okay, from at altitude 0, it increases up to 213,000 and it will be plateau at above 100 times 10 to the power 3 altitude. So the effective exhaust velocity as defined in the earlier equation, equation 6, applies to all rockets that thermodynamically expand hot gas in a nozzle. For constant propellant mass or constant propellant mass flow in equation 14, which can be modified to the following expression, equation 16. The exhaust velocity, which will be equal to the V2 plus the difference between the pressure inside the chamber and the atmospheric P3 times the area 2 divided by the mass flow rate. And equation 6 shows that the exhaust velocity can be determined from thrust and propellant flow measurements. When P2 equal to P3, okay, pressure inside the chamber equal to the atmospheric pressure, the effective exhaust velocity C is equal to the average actual exhaust velocity of the propellant gases V2. Okay, so when P2 not equal to P3, then the effective exhaust velocity will not be equal to the propellant gas velocity. When the exhaust velocity, effective exhaust velocity C equal to V2, the thrust from equation 14 can be rewritten as equation 17. The characteristic exhaust velocity has been frequently used in the rocket propulsion literature. So its symbol C star is defined as the expression 18. Okay, this is the characteristic exhaust velocity. The characteristic velocity C star is used in comparing the relative performance of different chemical rocket propulsion system, designs, and propellants, and it is easily determined from measured data of the mass flow, the pressure inside the chamber, and the area at the throat. Okay, so it relates to the efficiency of the combustion and is essentially independent of the nozzle characteristics. Right, and the specific impulse IS and the effective exhaust velocity C are functions of the nozzle geometry, such as the nozzle area A2 divided by the AT. Right, that's all for now. I will share with you in the exercise given later in the following video. Thank you and have a good day. Assalamualaikum warahmatullahi taala wabarakatuh.